Hello everyone. In one of my previous videos where I talked about GD&T, I kind of introduced it in general, but in this video I want to talk about why GD&T, not what is GD&T. So I want to talk about why GD&T is important and why we should not just go with adding the plus and minus to the linear dimensions, right? Or radial dimensions, and we should focus on features, right? So GD&T is a feature focused tolerancing as opposed to dimension focused, right? So let me add that for you here, that GD&T is feature based tolerancing, not dimension based tolerancing. Okay, this is an important thing that we need to keep in mind. That's the major difference. And you might say, fine, they are different, but what does it bring to us, right? So let me show you. One of them that is mentioned in the previous video, but I want to mention it fast one more time, is functionality. So we put the tolerances based on functionality. So here, let's say you have a mirror and you have a frame, and this mirror has to sit in the frame, and the mirror has to be a straight mirror, right? Because you want to see yourself. Let's say it's for bathroom, and you want to see yourself real size, not made bigger or smaller. And these are the dimensions and the tolerances for it. So on the length is 1500 plus minus 2 mil, in the height 900 plus minus 2 mil, and thickness 2 mil plus minus 0.1. Okay? And now, if I give you two different mirrors right out of the company, right out of the manufacturer, one is the one on the left, for which let's assume that both of them, their width or length is made according to the tolerance. So their length is no problem, but if you look at their profiles, one is straight, almost very straight, and the width of it is within the tolerance, but the thickness of it is out of the tolerance. So if we just want to go based on our plus and minus, you say, hey, this one is made thicker than 2.1, which is maximum dimension, so I'm going to reject this, right? This is going to be rejected. On the other hand, this one that is curved, and I measured the span of it here, right? Because really that's a span here, and it's within the limits, and the thickness, I measured it also, is within the limits. I'm going to accept this one. While in reality, this one is a curved mirror, which is going to show you basically smaller or bigger, and this is a straight mirror, which is going to serve the purpose. And if this frame allows this extra thickness to be used, then in reality, I should take this one and I should reject this one. But you see here, I'm doing the opposite. So maybe instead of doing it this way, a good idea is to have this mirror and maybe give it a little bit more room for the thickness, or what we really care about is we can use a what? We can use a flatness, right? So we can use a flatness, and flatness also basically controls here the size too. Okay, so maybe we can put some numbers here, right? Or we can use some straightness if it's a 2D feature. In this case, it's the 3D, so I use a flatness, right? But here I can do that one, and here I can go with some basic dimension and say, hey, this basic dimension, I want this to be what? 2, and then I allow for so much of tolerance here. I don't know, maybe like 0.1 or 0.2 or something. Okay, and that way I can control how thick it is, and I can control how curved it could be, or how basically how much ups and downs it can have, right? So you see, that's one thing. The other thing is the parts that are interchangeable, and because there is no ambiguity in manufacturing. So here, let's say I have two parts. This red part that goes into the green box, and The dimensions I provided with the plus and minus form are, as you can see, 1.998 plus minus 2000 and 2.004 plus minus 2000. Right, so clearly you see this is smaller than that. And in the height, similar thing, 1.948 plus minus 2000, 1.504 plus minus 2000. So you see clearly it's a loose fit, and the red should definitely fit inside the green, and I have some diameters too. Well, it does as long as what? All of these angles are made perfectly, because here in our general tolerance note, we say all dimensions, let's say, are in inches, and the angles are plus minus 1 degrees unless otherwise specified. So here, and most of the time, this is the best you can do for angles plus minus 1 degrees. Most of the time, you don't have equipment to go below a degree. So here you assume that, yes, this one will fit into that if all of these angles are made what? At 90 degrees, right? Let me use a different color. So if all of these angles are made perfectly 90 degrees, right? And if all of these surfaces that I can see are perfectly flat, then yes, everything would work. But in reality, and here is a little bit exaggerated, but in reality, you might get something like this one, where this angle is only 1 degree off, like 89 degree to 91 degree, right? It's a little bit off. Again, it's exaggerated. And if you look here, the dimensions might work, okay? The dimensions might work, the angles don't. And if you look at the surface, it has ups and downs, right? You see the surface is not perfectly flat. So in this case, these ups and downs and these angles, and not only that angle in 2D, in 3D also, when you look at the side view, instead of this axis being 90 degrees with respect to the bottom plane, it's also at 89 or 91 degrees. That is another one. So all of these deviations will make your part to be what? Not be able to fit inside that green box. Although you might grab the caliper and measure the width and height from 2 points and say, hey, look, these dimensions fit my tolerances, I'm good, right? Right? So you say, hey, this is 2, it's within the limits, and this is 1.5, it's within the limits, and I'm good. But when you put the red part in the green, you see it doesn't go in. Why? Because again, there is no consideration for all of these geometric relations, including perpendicularity, flatness, and so on. So another approach is say, hey, these are the dimensions I would ideally like to have. These are basic dimensions. You don't put any tolerance on them. Instead, you put the tolerance on what? On the profile. And you say the profile that you give me with respect to this ideal rectangular profile, the best it can have offset is what? 2000. No more than 2000. Okay, then if this is 2000, right? If this is 2000, then 1000 outside, 1000 inside, at best, it can be off on both sides. So the maximum dimension of it is going to be 2. If this is that one plus that number. And then if you add that number to this one, also it is going to be 1.5. And with these two dimensions, you can guarantee if this outer box is made properly also with a similar profile thing, it would definitely work. Okay, so you see this way, not only manufacturer knows how much deviation they have on the shape, in addition to dimensions, they also make it such that the parts are interchangeable. So if you make them or somebody else make them, or you make them in different times, you make sure they always work. The last thing, which is very, very important and kind of mentioned in the previous step, is inspection and assembly. So if you want to put the parts together, you want to know how they are assembled and how they are inspected. Okay, let's first talk about assembly, then come back to inspection. So let's say here, and actually they're kind of related. So here I made this part, which is kind of like a S shape or something, right? And or a jog, you might call it. And let's say the height here is 20 plus minus 0.3. So and it is going to go inside this chamber here, inside this pocket, inside this hole. And when the part comes out, this angle here is not going to be perfectly 90. It's going to be a little bit more than 90 degrees, maybe 1 degree off or something. So it's made a little bit with an extra slope here. So the person comes in and puts the part in the hole, and what they do is they put this surface, they align it with the bottom surface of the hole. And when they do that, you see the upper surface is sticking out of the hole, so it cannot go in. Okay, so they say this part is bad, throw it away. Now somebody else comes and say, no, well, why should we insert it like this? It's the same part, as you can see, it's the same as this, but they would align the top surface, the top part of it, with the top surface of the hole, and they slide it in. And you see that there is some gap here, but the part could go in, so they say good. So here this one says accepted, this one says rejected. So which one would you basically take, right? Because each one is assembling it a different way, and probably you experienced that, right? A part that does not go into something, maybe if you just manipulate it and move it and rotate it, maybe you can finally get it in. It doesn't mean you did it correctly, but you could put the parts together. I mean, like pass a part through the other one. But here, using GD&T, use a datum. Here, with this datum, you say, hey, datum here is the bottom surface. Why is it the bottom surface? Because in my assembly, I really want this guy to be in contact with the bottom surface. So you put some importance on that and say, hey, that is an important surface. And that surface also has to be flat because it's a datum and it's used in assembly. And then you provide some basic dimensions for this height, and then using a profile again, you allow this maximum deviation to be at most 20.3, because again here if you look, this deviation is 0.6, so it is going to be, with respect to this surface, it is going to be half of that 0.6 above and half of that 0.6 below. So 0.3 above, or the 300 thous, and 300 thous above. So the maximum dimension is going to be 20 plus 0.3, so it's going to be 20.3, and would definitely what, if you make the part according to this GD&T, it is definitely going to work. Also, another one is here. So let's say this is a bracket that you have with 2 holes, and these are all the dimensions with pluses and minuses, and the part comes out, again with exaggeration, something like this bottom one. And this bottom one is clearly different than the top one, again exaggerated, although it's the same part, but, well, the manufacturing board is not perfect. And now, let's say you are the inspector, you grab a caliper and you want to check whether this dimension 1.18 plus minus 5 thous, is that made to the tolerance or not? Is it to the spec or not? So what would you do? You grab the caliper, now you want to measure that distance. How would you measure it in this part here? So there are lots of different ways you can do it. Somebody might say, hey, it's the distance on this edge between this point and what? This point, and so they go for this guy here. Somebody might say, no, that's not really that. It's the distance from this point to what? To here, right? It's from this edge basically to this edge, and they might go what? They might go, let's say, for this dimension here, right? Okay. Or somebody might say, well, no, it's really from this point to this point, these two. And they go for this dimension. And there are other ways that you can interpret that. And you clearly see, if you look at these dimensions, they are all different from each other. One is shorter, one is longer. So one of them might fit that range, one of them might not. So some people might accept it, some people might reject it. That's why these pluses and minuses could be ambiguous when you want to talk about their assembly, their inspection, and so on. but using datums and references and using these GD&T symbols like position, like profile, and so on, you should be able to exactly specify everything, the features of size, the regular surfaces, and so on. And you make sure that you just provide so much tolerance that the part is functional rather than you just put a ton of tight tolerances, which makes the manufacturing cost higher. So hopefully this video enlightened a little bit about the GD&T and why it is important. And by the way, a lot of the material that I used and use from now on, they come from this reference here. This is a very, very beautiful book, GD&T Pro 2020 by Scott Newman. Okay, or Neumann, I'm not sure how to pronounce his name. If it's a German, you would say Neumann. If it's American, probably say Newman. And I used his classes of GD&T in ASME, and he's an amazing instructor on GD&T. I learned a lot from this person. And the book that he authored with his company GD&T, that's an amazing book. So if you want to learn more on GD&T, feel free to buy this book. I mean, like, it's 120 or something on Amazon, but it's absolutely worth it. So this is my reference here, or one of my major references. Okay, so hopefully the video was useful to you. I'll see you in the next video.